Alright, so the first thing I'm going to do, I'm going to come in here with a green pen and just identify my polarities. You know, this power supply should be apparent and known, but I'm going to go ahead and just, based on my power supply and its position and configuration in the circuit, I should be able to easily identify the polarities in this circuit, so we'll just go ahead and do that. Alright, so there's my polarities, or my voltage polarities. Okay, so now when I do my loop equations, so I'll just start right here in this corner. So I always just start, you know, in the bottom left corner, just out of habit. It doesn't really matter, but I tend to just do it exactly the same all the time, and then it's just less thinking for me to have to deal with. So basically what I'm going to do is I'm going to start here, work my way around this closed loop in a clockwise manner, and whatever polarity I encounter, I'm just going to I'll just write that down, and I'm going to be creating a voltage loop equation for this loop. Okay, so starting here on my little corner, my little dot where I've identified that I'm going to start, I will just start traveling up that path around the loop. First thing I encounter is a minus on my power supply. So that power supply is a known voltage with known polarity. So let's just start a Kirchhoff equation. So Kirchhoff is always any closed loop, so the voltage around any closed loop will always sum to 0. So 0 equals, now I've traveled up my path here, minus 9 volts. Okay, I just happen to have that number, so I'll just use it. You could do this with no numbers and just say minus VT. That would be fine. Okay, so I'll continue past the power supply up around this path, coming around, and now I come down and I encounter the positive side of R1, so plus VR1. I'll just keep on traveling past VR1. I'll continue. I'm on this large, the taller loop, the one on the left. I go past this node, I encounter the plus side of R2 plus VR2. And essentially I'm back to where I started. So I've gotten back to my little dot that I've indicated, and I've got myself a Kirchhoff voltage equation. Now I could manipulate this, and basically I'll end up with 9 volts equals VR1 plus VR2. Okay, so I could solve for VR1, I could solve for VR2. Right now both of those are unknown to me, but I do know that the sum will be 9 volts. So that's something to think about. Okay, so now I have some other loops as I've identified. Let's do the outside loop. So I'll start and end in the same spot, but I'm gonna, instead of going through R2, I'm just gonna go all the way around the outside of the circuit and include R3. So 0 volts equals, again, countering the minus 9 volts. Okay, I'll keep going around, plus VR1, and I'm going to go around the outside this time, plus VR3. Okay, so now the same thing, basically 9 volts equals the sum of VR1 plus VR3. Alright, so this will be my, I'll just identify left loop, outside. I'll just go ahead and do this little right side loop too, so I'll start here on this node. Okay, start right on that node, and I'll say 0 volts. Okay, no power supply in this loop. Coming up, and I'm seeing the negative side of VR2 coming around the up here and back down. I'm encountering the positive side, VR3, and basically I'm back. So there's only 2 components in that little right side loop. Okay, so now this one's interesting. So now I can see that VR2 equals VR3. And so some of you, if you're familiar with the rules for parallel circuits, we see that R2 and R3 are in parallel, and so we know that those, whatever that voltage is, it will be the same, and our little equation here confirms that that is true. Now, interestingly, I know that VR1 plus VR2 equals 9 volts, and VR1 plus VR3 equals 9 volts. So my two other loop equations are basically equivalent. So I could say that VR1 plus VR2 equals VR1 plus VR3 equals 9 volts. So those are all equivalent equations, so that's, you know, interesting and nice to see. But I still, you know, I may not at this point have enough information or have a plan really to figure out, you know, which of these equations I'll want to use, or what I'll be able to substitute in and try to figure out what to do next. But I've got my voltage loop equations. So the next thing, as I told you a moment ago, I'm now going to start looking at current node analysis. Okay, so I've only got one power supply, so I could identify this current here leaving the source as the I total, and I could also identify the current coming into the one power supply or the one source as I total. Alright, so that current comes along here, travels through this component from negative to positive, R2 from negative to positive, R3 from negative to positive. Okay, so I'm working in electron flow. Okay, there's our current total. I've got some current going that way and current going that way. So I've drawn all my paths. So I total comes into this node down here, and this current leaves and this current leaves. So the sum, so Kirchhoff's current law says that the sum of any currents entering a node will equal the sum of any currents leaving a node. So as I said before, I've just identified this current in this main branch as I total. This current going through R2, I'm just going to say, we'll just call that I of R2. Oops. And then this current here that's going through R3, we'll just call that I of R3. Now that one's a given right here, which is part of why we're going through this detailed analysis. So that current, IR3, and that current returning to this node up here, IR3. So it's all the same stuff. Okay, so let's just look at this node right here. And what's going in? Well, IT is going in. And so that's all that's going in. So that equals the sum of everything leaving, which I've got IR2 going this way and IR3 going this way. So the sum of those two things. Alright, so IT equals IR2 plus IR3. Okay, so that takes care of that node. Now let's identify this current here just as IR1. And notice something interesting here. Well, I've identified this current upstream here as IT. Right, so IR1 happens to be seeing the total current, so let's identify that. IR1 equals I total. Okay, so that's interesting. It just sees the total current. It's directly in that main path. Okay, let's look at this node, which is our only node we have left. So what's going into it? Well, I've got IR2 entering, and then I've got IR3 entering. So IR2 plus IR3 entering, which equals the sum of what's leaving, which is just IR1, which I've identified as IT again. Alright, so now we can see that these two equations basically are just exactly the same. I've only got one place where the current splits as it leaves the source, and then those currents will join back together and be IT. Okay, so basically I think I've identified all my voltage and current relationships in the circuit, so I probably have more than enough information to solve this circuit. I just have to decide which voltage equation or which current relationship that I'm going to work with, and I will go ahead and see what I can do to try to solve this thing.